Good morning, good afternoon, good evening, everyone. Thank you for joining us today and welcome to the DAS RCN webinar on instrumentation. I am Casey Adderhold from Incorporated Research Institutions for Seismology. IRIS is a consortium of universities and an NSF-funded science facility operating programs that enable Earth scientists to perform advanced research in geophysics, particularly in seismology. This webinar will be recorded and archived on the IRIS Earthquake Science Presentations webinar YouTube channel. Should you have a comment or question as the webinar unfolds, then please clearly and concisely type it into the Q&A box, not the chat box, on your Zoom control panel. At the end, we'll read your name and question to the presenters. If similar questions have been asked, we may combine or skip them. If the webinar happens to crash due to Zoom or internet issues, we will reboot it. Just click the webinar link again. Automatic captions are available to be turned on and off on your Zoom control panel. Use of distributed acoustic sensing is rapidly expanding in our community, prompting the initiation of a research coordination network to facilitate workshops, tutorials, and other opportunities for sharing ideas and resources. This is one in a series of webinars on different topics within distributed acoustic sensing. I'm going to pass this to Dr. Yingping Li now to get us started. Yingping?
Okay, thank you for joining us today. My name is Yingping Li, and I'm a co-leader of the Instrumentation Working Group of the NSF-funded DAS Research Coordinated Networks. Today, we'll hear from some of the vendors participating in this group as part of the series of webinar showcase by the DAS vendor and the DAS service providers. This will enable a platform to bridge users and vendors, leading better communication among the DAS societies. We welcome others to get in touch if they would like to present at one of these in the future. Our first speaker today is Oleg Valishin from Sercel. His presentation title is Monitoring of Near-Surface Conditions of Railways Using Distributed Acoustic Sensing. Oleg Valishin holds a master's degree in the petroleum engineering from ENSPM IPF School, France. After a few years within Schlumberger in different field operation and management responsibility, he joined Sercel in 2007. He successfully held the position for deputy managers and the manager of the downhole seismic 2 business units, Sercel Business Innovation Manager, and currently is new venture directors. So Oleg, is on your hand. Go ahead. Thank you.
Perfect. Thank you very much for the opportunity to present it. The idea here today is to present the different use of technology and also to share, disseminate the knowledge of what, on our humble opinion, has been working and not has been working, and how we see the way forward with it. So hopefully the presentation can be seen. So just a quick introduction. So Sercel is a part of larger CGG group and manufacturing mostly on oil and gas seismic exploration equipment, onshore, offshore, and downhole. And since recently, we also heavily introducing ourselves into infrastructure business, both through Sercel and CGG, and also in end of May, we bought a company here in the United States, which is called Geocomp, working in infrastructure monitoring. So we have different type of technologies that they're working on infrastructure market. Well, as Sercel, we brought these 2 technologies. We'll talk about more detailed about SCAN, which is a near surface geophysics, but we also use S-Links, which is for monitoring the structures. This is using a different type of technologies, but one of the seminars that we'll be like to talk in the future as well is using S-Link technology in combinations with fiber optic sensing. And we already done a few experiments, and we'll be participating in sharing this knowledge. We'll talk about SCAN, which has been developed specifically for railways, but now it's being used for other for applications as well. We also work for some other areas. This is not commercial technologies, such as monitoring the railway conditions, monitoring the natural hazards for such as the rock drops, using the passive seismic for the sea dikes. All of these 3 domains under development also use distributed acoustic sensing, and we'll be happy to share our findings as we go forward. So a little bit of an introduction, because it's important to understand as a basis of what we are doing. For near-surface geophysics, the different ways to look on how we can identify the hazards, such as sinkholes or weak layers, liquefaction layers, and so on under the railways. The method that we have developed together with the French railways is using the surface waves propagation, surface waves generated by the train passage and captured by different type of sensors, including distributed acoustic sensing, to give a full picture of what is happening in a near surface. These applications can be typically for the near surface for railways, so usually limited to about 15-20 meters deep. But using other meta type of processing that we also use, it can be used for the deeper conditions. So typically how you do the measurement, so you can install different type of sensors. So it can be a temporary installation, and even if you go for the definitive distributed acoustic sensing measurement, we usually go with a temporary installation using electronic sensors, such as you can see on the left, which is called the nodal systems, and which can be geophone or MEMS accelerometer with a battery and power and electronics for recording the data. Or you can also do the permanent real-time acquisition using the keyboard electronic system of fiber optic sensing. So how it works, usually depending on the needs of what is required, the problem that is required that has been identified by the customer, the depths where the problem may be happening, the lengths, and so on. We define the survey design. We define the right type of equipment that can be installed to address this kind of acquisition. We have an automated processing that would allow to process the data that has been done on both on scan, temporary scan, or permanent monitoring, and doing all the appropriate quality control, and then produce the results. And the results can be also in terms of report, pictures, or even at the daily follow-up of what is changing with following up the velocities changes over the time. And this data, being obviously seismic not being a silver bullet, is being concatenated with other types of measurements such as geotechnical investigations or drilling. So initially, this technology has been developed for the railways, but now it has been rapidly expanding in other domains such as mine tailings, earth levies, permafrost, and so on. It also allows to see the changes over the time. So you can, example here, one of the projects where we have a multiple years installation for one of the railways, and you can see the changes happening over the time. And we need to compensate actually as the changes of humidity, for example, or temperature to ensure that the image that we provide is accurate. So this is an example of one of the projects. This is with electronic sensors, but I'll show you in a second what is happening with distributed acoustic sensing. This is a typical image that we would provide with electronic sensors for 2 tracks for railways, meaning high precision image of surface velocities underneath the track. So that would allow to identify the areas, for example, that you can see in red circles, which are the weak areas, and that have been confirmed by the drilling by the operator in this particular case, and that cannot be identified by normal methods such as ground penetrating radar or less sensitive conventional multiple analysis of surface waves. The big interest of this kind of technology is there is no human intervention, especially in case of monitoring, so that doesn't require stop of the trains. So depending on the technologies, there are different ways of addressing it, and this is where we're coming to distributed acoustic sensing. If we talk about the short tracks of temporary installation, electronic sensors is probably the best. It's going to be more simple, much more simple to install, and so on. But if we go to the very large stretches of the railways to be monitored, the answer comes very clearly. It has to be distributed acoustic sensing, because the electronics becomes a little bit more expensive. In some of the cases, the longevity, which is requested for the monitoring, can be 10 years more. So in this case, for these large stretchers, the distributed acoustic sensing is a very strong interest, and this is why Sercel has been working for the last few years on this domain. So we work on different ways to do it. When you talk about distributed acoustic sensing for geophysics for the railways, there are different ways to do it. One is you have a specifically buried fiber next to the railway. That's the best way to go. And there are different types of fibers and different types of cables that can do it. Or you have the existing fiber, which most of the time is in a conduit and doesn't have necessarily the good contact with information. I'll show you an example with all of them. So one of the best way to do it is a specifically buried cable, and also in sometimes using the different type of cable to increase both the sensitivity and also to address one of the problems that we can see on distributed acoustic sensing related to the fact that it's a one component measurement. So one of the things that we have done is we used on one of the projects, we used the helically wound cables with a pitch of 60 degrees buried in the ground next to the railway. And we can see the results of the DAS with a very sharp resolution on the left compared to the 3-meter resolution on electronic sensors on the right. So helically wound cable manufactured by Sercel, we do it in a different diameters. This was within 3/4 of an inch of the diameter that was buried next to the track. 60 degrees pitch seems to be working best for these particular applications, and not always. Sometimes straight fiber will be enough to give the good responses. But in some cases, we have seen that helically wound cable may be a right answer to be more precise and more specific to address the geophysical imaging of a particular type of a track. So this is an image also that compares the some of the sections that we have done using the helically wound cables, the images on the right and in the center compared to the electronic sensors. And you can see one of the clear advantages that is coming on also with the distributed acoustic sensing. You can much more easily cover the large stretches of the formation. So if you go to the concrete case studies beyond the theory, this is an example of one of the operators who had a freight rail derailment. So there was a problem, there was a strong subsidence that ended up in a derailment, and actually the section of the problem was more than 22 kilometers long. So that was addressed in 2 different ways. The first way, with Sercel has deployed with our local partners, we deployed the nodes, the electronic sensors that allow to see the high resolution pictures on 2 different zones and to identify the areas that we confirmed by drilling as a weak layers. But then we had to de-risk a monitoring of a much longer section, and this is where distributed acoustic sensing comes into play. And what you can see on this particular image, you can see the images on the bottom, where you can see very much condensed. It's a 500 meters on a few centimeters, so you cannot see much. But we have done 2 sections of the 500 meters using nodal sensors, and then we followed up by monitoring with fiber optic sensing on the range of 3 kilometers. So that allowed to do the 2 things. First of all, it confirmed using distributed acoustic sensing, this was a specifically buried fiber, straight fiber, allowed to give first level of knowledge about the formation, and it was confirmed by a more high resolution nodal survey. So it was not as sharp as the image that was derived by the electronic sensors, but it was still good enough to have the first baseline, and that would allow actually to having, for example, 1 trimester measurement on this particular section to see the changes that are happening. It also allowed to identify the weaker zones on the different part of the sections using distributed acoustic sensing, and we proved that this technology is good enough for that. As usual for distributed acoustic sensing, the coupling of the cable and the quality of the cable is primordial. And in this particular respect, you can see the red boxes on the top. This is where we had a poor coupling that was straightly related to the quality of the data that we were getting. This is an example of an existing fiber from another operator. So existing fiber has a lot of challenges because the existing fiber, it's a telecom fiber. It's not necessarily designed to be for geophysical purposes. It's a straight conventional fiber in a thick cable. And as this thick cable is sitting in a conduit, not necessarily in very good contact with information, which is critical for the geophysical measurements. So in this particular respect, we have seen an example where we have this in the large section of the rail being monitored using this conventional fiber. And we can see that this section on the left, we have done very poor results. And very poor results, and they've been confirmed by analysis of what physically happened there. It was related to the fact that conduit was different, and we had a very poor coupling. As a result that they had delivered were not satisfactory. But where in this different part of conduit, which is looking on the right side, actually the results were very good, and they confirmed both by the prior geological information. So that opens such a vast possibilities of using existing fiber, which is in a conduit, for monitoring the near-surface geophysical conditions, provided that the coupling is right. So some quick conclusions here, and hopefully that will be useful to the audience, is that I think that one of the things most of the people, there are some people working in this direction, but we confirm it by physical measurements in different countries that DAS can be used for near-surface geophysics for these applications for railways. Clearly, quality of processing will be very primordial, quality of the cable and the fiber and the way how it's buried will be very critical. We have seen, and that has changed over the time, there are many vendors now on the market, and the different vendors propose different technologies for the interrogators, some of them better for something, some of them better for something else. But overall, we have seen that you don't need a very scientific interrogator. Good commercial interrogators can deliver good results. However, the key things, especially for the geophysics, and especially in this kind of respect, we are trying to image something small, and they're very small variations. So we need to work with a very high sensitivity, and we need continuously to make a trade-off between using a gauge length, which has to be very short as possible, to image something, to image something small, and not to have to give a sharp image as we can provide, and the reduction of the sensitivity with the reduction of the gauge length, which is characteristic of some interrogators on the market. So we need to find a compromise. The high sensitivity cables is potentially a way to go. For most of the commercial projects that they're working on right now, you don't need high sensitivity cables, but we're using high sensitivity fibers. But having an optimized cable for high sensitivity can be a big differentiator. And this is for, at least for our side, this is where we're going to. Having the right burial, of course, that's a primordial to obtain, to get it right. And we are glad that there are vendors, and I think one of the FEBUS will be presenting their advances in a minute. The vendors are continuously improving the quality of interrogators to allow to get the better signal to noise ratio that will get better processing done. Helically wound cable is not a silver bullet, but is a solution, and we have seen it in several conditions where it can address the problems of fiber directionality, having the fiber blind to some of the signal, especially for the horizontal fiber on a surface. So having it buried everywhere probably doesn't make sense, but having it in place for several areas where the prior modeling shows you need such a cable makes a big difference. So using the DAS is possible, but you need to be aware of the limitations. So everything that we have mentioned, because there's unfortunately some of the vendors on the market that do not disclose to the customer this kind of limitations, and it ends up in a commercial of technical disasters in terrain. So the final operator or the partners in the ground have to be clear of the limitations are there to make sure that the distributed acoustic sensing continues to be used for this infrastructure project with success and with a high confidence to make it a more widely accepted technique. Well, and the last and probably most important thing, we receive a lot of questions saying, what is better, electronic sensor or distributed acoustic sensing? I think it's like asking the question, what is better, a bus or a car? Well, both are good, depends what you want to do with it. In some of the cases, electronic sensor would make full sense, both from the realization point of view and economical sense. In some of the cases, distributed acoustic sensing is the only way to answer, typically the large distances. So in some cases, actually, we go with a combination of both, because not necessarily full time, but you can also compare, benchmark, and adapt the best technology. The final thing is not the technology, how you're going to acquire the data, but the final result that you give to the customer. And actually, something that is also important to the seismic community here is to incorporate, it's difficult to message to hear, the seismic is not a silver bullet. You need to incorporate other measurements, you need to incorporate the geotechnical knowledge, and particularly working on infrastructure projects to make sure that what you deliver to the final customer is a full product that can be used in the real world. Well, that ends my presentation, and it is intended as an update of what is being happening with distributed acoustic sensing in railways. As I mentioned, there are a few other applications we are working on. We would be happy to share with this group, and hopefully it was useful for the audience. Thank you very much.
Thank you very much for Alex for his nice and informative presentations. So any questions, you can type in your questions in the Q&A. So then we just ask Oleg for a few questions. Okay, I just not really question, just comments and maybe another questions. The one thing is it's very good to see you use this DAS system to get velocity structure information along the railroad. So most people just concentrate the railroad monitoring itself, but actually you give some fundamentals on the safety for the railways, because if your base have some problem, that could be even worse than the railroad itself problems. So a second thing is, since you have set up the FEBUS along the railroad, most time you're recording the transportation for the railroad. But I just wondering if you have a chance just recording the earthquakes.
Absolutely. Well, the first thing that it's we see that on different projects, actually having a fiber just for geophysics sometimes is justified because it's really the problem, the geological problem is there. But once the fiber is there and we're recording the data, it makes full sense to get the additional information such as the train tracking and all the other services that can go along with it. And so that's a bigger value to the final customer. Second thing, yeah, obviously earthquake. Yeah, they depends on the region. There's regions which are not really interested in this kind of conditions. There are the regions that are definitely interested in that. And they also incorporated the knowledge that is coming from this kind of recording in the design of the seismic resistance of the structure, the early warning systems in combinations with some existing, for example, here in the USGS or the other systems.
Okay, we have one question by the Jiaji He. Oleg, thank you for your informative presentations. What frequency range should the interrogator be able to sensing in order to perform near surface imaging?
Most of the time, the most useful frequencies are effectively between 0 to 200 hertz. It's very rare to have the high frequency signal. We use it for some other very specific applications, but usually, yeah, it's a quite low frequency versus what DAS interrogator can achieve. So we're staying between 0 to 200 hertz, and we can go higher if it's required for processing.
Okay, great. We have another questions. Euro Star Robot. So, Oleg, thank you for the excellent presentations. When you are talking about electronic sensors, what is about geophones or MEMS? If both, what is better?
We have seen, depends on the applications. We manufacture the equipment with both the geophones and MEMS. In this particular respect, we'll be using the MEMS for two fundamental reasons. First reason, the MEMS is an electromechanical device. Sercel is manufacturing the MEMS, so it's the third generation now. We have the MEMS that has two particularities. One, it has the lowest noise floor on the market. So we actually sell it to some academia, as a matter of fact, for scientific research because of its performance. And it allows you to have to work recording from 0 hertz. And it's important for us to get the reliable signature of the low frequencies. That's reason number one. Second reason is that we have noticed, especially in the railway sector, that having the MEMS allows you to avoid this electromagnetic parasite waves. Because if you're using a geophone next to the electrified track, whenever the train will pass, you're receiving a lot of electrical noise, obviously that you can remove in filtering, but you are risking also to get some useful information out of the data when you're doing that. So having the MEMS actually effectively solve this problem, and we actually have the systems installed underneath high voltage lines and recording the data. So MEMS would be preferred to make a short answer.
Yeah, great. So do we have further questions? And I think the Alex also made one greater point at the end of his conclusions. Just say when we have the DAS, that's great, but also I think if we have both DAS and discrete sensors, why not we use them both to get both advantage from them. So I think that's another things probably we should be discussing among the societies. The distributed sensor is great, but also they have some disadvantage right now. So probably we can combine something together, then we can get a little better. Okay, we have another question here. Gabriel Basnello. Can you please comment on the directional sensitivities of the fibers with the parallel to the rail track?
Yeah, that was one of the issues. In our processing, we can work with a straight fiber. So straight fiber, as you know, that there is a problem of orthogonal sensitivity with an angle, orthogonal waves or P waves, plus minus angle of 15 degrees. There's a lot of publications around it. So we incorporated this in the processing to make sure that we get the useful results out. But some cases we need to image the zones, and that forced us to use the helically wound cables. Luckily enough, manufacturer actually we sell this kind of cables in the industry, so we had easy access to it. So we have a few projects installed with helically wound cable, and the answer is that would allow to. It's not a 3-component measurement, but it will allow you to combat this problem of directional sensitivity, but you don't need it everywhere. And most of the time, processing can handle all of the situations in normal conditions.
All right, I think we have someone with their hand raised. Morten, are you able to unmute and ask your question?
Yeah, so
you should have the ability to now.
Yeah, but motion, please ask your question. You have mute yourself, just unmute and speak. Morten.
All right. In the interest of time, we might have to move on, and but if you have that question, you can of course add it to the Q&A box.
Okay, so probably the time we just switch to the second speaker, so we are perfect on the timing. So thanks to Oleg for control the time perfectly. And all right, so our second speaker is Vincent Lanticq from FEBUS Optics. So the title of his presentation is That's Frontier and Complementary with Brillouin-DSTS and Raman-DTS. So Dr. Vincent Lanticq graduated his Master's of Science from Institute, the Optic Graduate School in Paris, and obtained his PhD from the Telecom Paris Tech. His research was focused in the nonlinear optic and the distributed optics fiber sensing. He was instructor for the students on the topic in the optic sensing technologies. During his 10 years experience of working on the field deployment of optic fiber sensor, he have incidentally various monitoring the systems FBG, Williams, Raman on a large range of the infrastructures, pipelines, desk, nuclear waste disposal, etc. 6 of this investigation have been patented. He's now leading innovation at FEBUS Optics as a technical director from 2015. So today we have both scientists and management from France. So Vincent is on your hand. Please go ahead.
Okay, thank you very much for introduction. Hello, everybody. Today I will present you as a manufacturer. I will present you some frontiers and evolutions of distributed acoustic sensing. And I will also insist on the complementarity of this technology with other distributed fiber optic sensing technologies, Brillouin and Raman, DTSS and DTS. So first, a quick presentation of FEBUS Optics at a glance. So we are French manufacturer of all the distributed optical fiber sensing solutions. We are based in France, and we put a lot of effort into R&D, and we are certified ISO 9001 for quality of production, research, and projects. So we are focusing on 6 main markets: pipeline monitoring, power cable monitoring, well monitoring, seismic and seismology, intrusion detection, and structural health monitoring. We have labs and facilities in France mainly, and commercials worldwide in Houston, Tunis, Abu Dhabi, and Paris. So we cover the whole range of manufacturing, supplies, and service around fiber optics sensing solutions, from preliminary study to installation and maintenance. Of course, we supply or rent our own devices, insisting in performance, cost effectiveness, robustness, and easiness of installation. So we should know that we have our own test center. It is located close to our headquarters in south of France. And so we have a large facility allowing us to perform a lot of experiments for pipeline integrity, for example, on cables. We have our own perimeter intrusion detection system based on our own solutions. We can simulate landslides and many more on demand. So it's a triple interest to have this facility is to qualify our devices and our solutions on fairly, let's say, close to the real field conditions. Second interest is to prove the technology to our customers, and the third interest is to perform on-demand and on-custom tests. So, general principle of distributed optical fiber sensing is necessary here to do a quick update on it, because I will present not only acoustics, but temperature and strain as well. So as everyone here should know or may know, it's an interaction between a pulse light sent by an interrogator, and that's what we manufacture at FEBUS Optics, interrogators. And so we send a pulse light into an optical fiber, located into an optical fiber cable. And then when this light propagates, part of the light is lost and propagated backwards back to the instrument. And since we know the speed of light into the optical fiber, we know perfectly that at the time t, the light is coming from a distance t. So that's how we locate ourselves into the cable. And then analyzing this light pieces by pieces, time by time, so we can have information on acoustics using distributed acoustic sensing, relay sensing. We can have information on temperature using Raman or Brillouin sensing, distributed temperature sensing. Using those effects, we have information on temperature. And we can have information on strain using only Brillouin sensing. This is performing distributed strain sensing. So at FEBUS Optics, we manufacture 3 of them. So Brillouin technologies, which is the B series, perform measurement on temperature and strain. I will come back on this later. A series, so FEBUS A1, for example, performing distributed acoustic sensing. And T series, Raman-based temperature sensing. And we have this nice device here in the right bottom part of the slide, which has the ability to repeat the signal, and it's compatible with the DAS and with the Brillouin-DSTS, so you can extend the range. So, of course, on the top of this interrogator, as I said before, we can provide the full solution, turnkey solution. So you have the interrogator part, which is here on the left. So you have the hardware and the software into the interrogation unit. And then you have this part here, which is solution dependent with the processing. And you have a server alert and a client. You can display alerts, or you can forward the alerts to third-party systems such as SCADA, DCS, or VMS. So now just focus on the DAS, so Distributed Acoustic Sensing. For us, it's called A1R. So you need tools to use DAS. So you need to protect your DAS and you protect your data you will or you have acquired. So you need an enclosure. So for this, we provide this type of enclosure with specially, let's say, designed damping systems here in order to not damage the data nor the DAS. And you will need, as you've seen in the slide before, storage. So according to the experiment you will do, you will go out, you will be in the field, so you may need a light solution. So for that, we have this kind of USB storage. Of course, it's less performant than other means, such as the NAS storage, which is very fast, but quite heavy. But this is a light solution, and it's something you can come back with in the plane, for example. So here, a part of the datasheet of the A1R, so the DAS, so of course, is measuring the phase. It's quantitative acoustic sensing. It's just not qualitative. So you recover, and you will see we recover the real strain signal on it. So the noise flow is measured according to MSPO2. So of course, it's dependent on the pulse rate frequency we will use and the gauge lengths. So the gauge length, it's adaptable. So this is the first nice features of A1R. So you can adapt the gauge length prior to the acquisition or after the acquisition from 1 meter to 99 meter. So that's a good feature because according to the signals to noise ratio or the wavelengths, the acoustic wavelengths you may have to measure, you can adapt these gauge lengths. So the distance range is 50 kilometers in the standard version. And then you have many more features. I want to insist today on the fact that now we have a dual channel. So meaning you have channel 1 and channel 2. We will see it's compatible with seismic acquisition, meaning it's not like one channel now and you do the job and then you switch the channel and you do the full job again. No, it's like you switch so fast as you can do seismic on both channels. So we have this A1R, which is the basic product, and then we can extend the range. We will see it's long range module on the top of it. And then we have this repetition module for REN, range extension module. So let's see how this fits. So first, you can tune the gauge lengths, so you can calculate your noise floor according to the gauge lengths. So of course, when you increase the pulse rate frequency, your noise is decreasing. And here, another parameter which is important is the optical energy. Of course, if you increase your pulse width, you increase the optical energy, you decrease the noise. So this has to be taken in account for what comes next. So here, as I said, we have this nice range extension module. So you have your A1R, you have your 50 kilometers of sensing. For example, you're sensing earthquakes, let's say. And then you put this range extension module. And the effect is tremendous on the next 50 kilometers. So if you turn on this range extension module, you go from this, its distance in y-axis and time in x-axis, to this same setup, but turning on the range extension module. And here you have the effect averaged over 200 meters on the noise floor here. So you can see you recover a good noise floor along a longer distance here. Then, as I mentioned, you have this long range module. So it's on the top of the DAS. It's such as you have a DAS with a longer range, and then you strictly increase the range, or you move on the right the range of your equipment. Meaning here you can measure from 0 kilometer to 80 kilometer instead of 50, 55. So it's more than 25 kilometers of increase of the range. So here we have to prove it's not just artifact or just noise tricks. So here you have a signal from small signal to big signal, and you can see the profile of this signal using this device with a long range module at 100 kilometers, and you have a 10 Hz signal from small to strong. And here you have the signal on the stretcher at a gauge length of 20 meters. And last but not least, you can use the long range module plus the dual channel. So you use a switch, and then you have 100 kilometers on the left and 100 kilometers on the right. So meaning here you will have 200 kilometers with just one DAS of seismic acquisition. So here you can see the evolution of the noise floor. Of course, here, just to prove it's not a trick, once again, you have the signal here at 100 kilometers on the right, meaning at 200 kilometers end-to-end on just one cable. And here you have signal at 2.6 nanostrain to 52 nanostrain. So from small signal to big signal. And here you see the effect into strain rate. So on the top of it, you can use long range module, you can use switch, and you can use range extension module. Of course, one limitation is the PRF, which is limited by the fiber length. So the longer the length, the less frequency, let's say, range you can achieve. So basically here, in such a scheme, we are limited to a PRF of 500 Hertz, which is the limit because of speed of light, basically. So then, what for? To do geophysics and seismic, because this is the topic here. So here you have an example of seismic data recovered offshore by just one system. So here, this is one shot, like air gun shot, offshore from platform to platform. And here you can see a nice signal into a cable, which is not a cable deployed on purpose. It's an electrical cable with telecommunication fiber in it, just to make one platform communicate with the other. So here you can see a nice and clear signal, basic signal from A1. So of course you can monitor earthquake. So it's passive seismic. So here you can see the plot, distance on Y, time on X of an aftershock of an earthquake of magnitude 5.6, quite famous in France because it's not every day you have this magnitude in France. So it was in Southwest. And we were, let's say, mobilized to monitor this fault here right after the magnitude 5.6. And then we measured a few days after this 2.1 in this fiber optic line of the real, let's say, this is telecommunication network, sorry, of 14 kilometers just nearby the fault. You have the fault in black, and you have here the fiber optic in green here in the map. So you can say, one can say, okay, you use a standard telecommunication network, so your coupling is not good, and that's right. So what if we deploy the cable on purpose? And that's what they do in the MONEDAS project, which is a French project from the National Research Agency with IPGP in partnership with Université de Paris. So they compared directly a coupled cable, which is buried, and a tight buffered cable at the Stromboli, and they put nodes along the cable, and then they convert the signal into particle velocity in order to compare differential response of nodes with strain rate measured by the A1R DAS. And so here you have the comparison. In blue, the node, in red, the DAS. And what you see here, it's similar. And the amplitude are matching quite well. You have here 4 types of events, 4 different events, and you can see there is a match. So when we see it's quantitative DAS, it's something. It's quantitative. It's same. Here it's same direction. You do your homework to convert on one direction your nodes and your DAS, and that's same. So that's a good indicator. Another one is the work done by a researcher of Karlsruhe Institute for Technology in Black Rest Observatory. So they plotted here 2 curves. It's strain curves, one from the DAS in red and another one from a strain meter they have for years at the observatory. And they detected and measured successfully an event coming from the opposite part of the hertz here, of the hertz is here in Acapulco, Mexico. So this just with the cable laid on the ground. So this is a quite nice results, and this shows you the ability for DAS to measure quite low frequency from 0.02 hertz to 2 hertz. We will see that for lower and lower frequency, some other instruments can take the lead. So about other instruments, just have a look on this comparison now between Brillouin-DSTS and Distributed Acoustic Sensing system. So as I mentioned before, we have our own Brillouin-DSTS. It's single-ended. It has a spatial resolution down to 1 meter, and we can oversample. The measurement duration is particularly small, meaning we can go down to 100 hertz. Here we will use it at 1 hertz to achieve a quite high sensitivity. So the sensitivity can go down to 2 microstrain, or H is missing here, and it's highly stable over time because it's frequency measurement. So here you have the Brillouin spectrum. So this is the raw data here in color scale, and this is the strain data interpreted from this color scale. So this color scale is frequency. So since it is frequency measurement, you can come today, do a measurement, unplug your fiber, and come back in 1 year, do the same measurement and compare them, which is obviously at least more difficult with the DAS. So this is an experiment to see the edge between the one equipment and the other, or let's say the complementarity of them. So we have a casing here in our test center, and we have 4 fibers glued, one on the top, one on the bottom, one on the left, one on the right. And so theoretically, if we bend it, meaning like we pull in the middle here, so we can measure the curvature using up and bottom fiber. And then if we double integrate this curvature, we should measure the displacement here at the center. So that is what we do. And we will do it with DAS and with DSS. And of course, results are same, but we will see when it's more accurate with one of the equipment and when it's more accurate with the other. So first, it's very important in this case, of course, I won't insist on it, but it's very important to have a good coupling inside the cable. So you need tight buffered fibers, and you need to have them glued to the equipment. Otherwise, it's very difficult on slow motions or at very, very low frequency to have something quantitative. So, of course, here we are in a perfectly coupled situation with straight fiber. It's not, we could have done, and we used to do it with wrap fiber, but here it's just straight, 4 straight spans of fiber. So this is the experiment. So here you have the cockpit. So you will see strain up, bottom, left, right, fiber optics. Here you will see the four fibers at the center location. Here you will see the bending strain in Y in red, the bending in Z, and the longitudinal strain in it's in black, so red, blue, black curves. And here you will see the calculated shape of the beam. And here the beam is a casing. So let's go. So here we are pulling up the thing, so it's going up. So you see the bending here, the bending here in Z axis, and you see the shape. So here we can pause. So here you can see, here we have elevation of 10 centimeters here from red to red, and here we measured 10 centimeters. So it works perfectly. It's like at school. It's 1 + 1. So now we go back and we are measuring this DAS currently, but it will be the same with Brillouin. No challenge on this. And here what we will see, and we are basically now back to the same state. So meaning something very neat and without any noise increase seen in that scale, meaning of 1 minute experiment. Sorry. So now what happens if we come back the day after? So in the morning, temperature is lower. So now we have a longitudinal, let's say, compression of the device. So it's negative thermal expansion, let's say. So here, everything is blue for DAS, everything is blue for DSS, same. And you can see a bit more noisy here on the DSS, on the Brillouin-DSS compared to DAS. But results are same. It's not the same day, so this day is colder. Trust me, behavior are the same. So that's no effect, because here you're measuring bending, so the blue curve and the red curve, and you see they are center to 0. So that's good, the experiment works well. But now what if we come back with the DAS, measuring continuously 50 hours later? So here you can see just after the first experiment, so 200 seconds, here, no effect, no noise, everything's perfect, flat curve. 50 hours later, noise here starts to increase. And this is a fact. DAS shows a very, very good sensitivity and very good repeatability in a short experiment. But if you do an experiment which lasts months or years, the noise will cover all the signal in this kind of experiment, except for high strain. And in this particular case, you can expect better results with Brillouin-DSS. Now, another comparison, another frontier for temperature measurement. Yes, DAS is measuring temperature measurement, but usually you use Raman-DTS, for example, in wells, to monitor temperature. So here you have a very, very nice sensitivity. In this particular setup, we reach 0.05 degrees of sensitivity. So usually you do temperature change measurement. So you can do temperature difference using trace to trace, and you use DTS for temperature in wells, for example, for production monitoring, and you use DAS as well. And there is a complementarity, meaning if there is an event of here, the liquid is coming up, so you see the temperature gradient here, and it's continuous with some energy plot you can do with the DAS. So this is traditionally performed data interpretation in wells. But if you want, you can go further. So here, let's say you have this temperature profile. So this is the depth in Y, the time in X, and in color scale, you have here the absolute temperature measured by Raman-DTS. And then you can do temperature gradient estimation in degree per second, and you have it here. With the DAS, if you do a traditional very low frequency energy plot, you will have this. So it will show you the gradient. But since you are quantitative, you can plot the data at very low frequency and use traditional conversion coefficient to get the temperature gradient, assuming there is no strain. It's like a slow strain data processing, but it's actually temperature. And you see a perfect match here. The scale are the same between both temperature measurement and gas measurement in terms of temperature gradients. So that's a very nice way to show you that we can measure temperature with gas with much more definition, much more sensitivity, but the same as for Brillouin before. If it is a very, very long-term experiment lasting years, you better use DTS. So as a conclusion, DAS is an extremely powerful device with a very high sensitivity to strain and temperature. It takes advantage of a large acquisition bandwidth. It's limited only by fiber lengths. We have seen that. But it suffers of a long-term drift due to low frequency noise, especially when you go to years, like -6 hertz, for example, which is like 1 month or maybe 15 days, something like this. Raman-DTS is sensitive to temperature and can return absolute values of temperature with calibration and measures accurately long-term variations. Same for Brillouin-DSS or DSTS, sensitive to strain, and which can be used for long-term monitoring. So there is an opportunity here for you researchers and for us to use a combination of devices to perform highly stable measurement with highly sensitive change tracking with the distributed acoustic sensing device. And that's all. Thank you very much.
Thank you very much for the Vincent. It's nice and informative talks, and we have more knowledge about the technologies. That's also say the development of the technologies. Most of that use really backschatterings, but then we also have the diversified to the Raman and the Boreas. So I think if you have any questions, please ask a question to the Vincent. So I have one question on your slides 20.
Yes.
Yeah, this is a nice recording for earthquake and the magnitude smaller than the 2.1. So you did not recording the main shock, right? So the 5.6.
No.
Okay.
No. So we were called right after the big one.
Okay,
so,
great. So another thing is I just noticed that if you look at your earthquake recording, just look at the first 1 second. So basically you see some noise levels higher than the other noise, other channels. So if that's any explanation on these things, you see this noise level is different. You can see some major noise.
Yeah, at some channels we have noise. This is because of activity. Actually, there is some. It's a road. You know, it's a long road. So you can have vehicles. You can have work. You can have many things happening while you're recording. So that's what happens. This one is it's quite clear compared to some others I can show you.
Okay, that's great.
That's why we use this one to show earthquake. But I have images of earthquake with 90 kilometers of fiber and a lot of trains and stuff happening all along the fiber. But here it's really quite clean in my opinion.
Yeah, I think the why I ask this question is because we find some in the BOHO data, we find similar things. We find the noise level change with depth. We just try to see if that's related to geologic structures. But we are not sure, but we have tried to see if that's any correlation between that. Since there's no other people raise question, so I ask another questions. We were talking about the Raman and Brillouin. You have measured both temperature and deformation. So for the slow screens. So what about with the sensitivity and the measurements you can achieve? Can you just measure the Earth tide, not just like Earth solid tide? That's a deformation for the Earth. But since that's a daily changed by the moon and sun, most probably by moon, but the temperature also changing. Temperature also have a daily change. So I just wondering what kind of solution you can use to try to separate these two.
Yeah, okay. So there are actually two, the basic, or let's say the usual way to separate temperature and strain is to use, for slow strain, for very, very slow strain, meaning static strain, is to use one tight buffered fiber and one loose tube fiber. Assuming the loose tube fiber is not sensitive to strain, only temperature. And so you subtract the temperature effect on tight buffered fibers using the loose tube measurements. Okay, that's the usual way. And you can do it with DAS as well. Problem is you can perfectly measure an earthquake, which is actually due to strain, with loose tube fiber, because it's quite high frequency, meaning it's more than 1 Hertz. So another way to do it for static strain is, if we come back to the Brillouin measurement. So you see this curve here, and we have this nice curve here. So we, to have this measurement here on the top, we use only the position of the center here of this color map. So at each position, we plot the curve and we find the center. We have this Lorentzian shape with Lorentzian peak. So we do a peak search on it, and we use only the location of the peak. If we use the amplitude of the peak, and we need to normalize the signal by another mean, but we have an instrument now which is close to be on the market, which is a prototype called D2, which can separate temperature and strain, having a look on frequency, but as well on power at each location here. Because here you see a decrease of the power, which is due to linear attenuation on the fiber. That's normal. That's normal way. There is no temperature. But if there is temperature change, so power will increase much more than if it is strain. So that's how you can discriminate temperature and strain using Brillouin scattering.
Yeah, great. Thanks a lot. And another question is related. You see, you can use the fiber to measure DTS and DSS simultaneously. So you will use the same cable, but the different fibers in that cable. Is that correct?
Yeah, or two cables.
Okay, all right.
Both are doable. Sometimes it's even sometimes the most expensive can be to use two cables instead of one complicated cable with one loose tube style fiber and one tight fiber.
Okay, great.
Depends on your cable supplier, let's say, and on your customer as well.
Yeah, also we're glad to see the technology development so fast. So right now I can see you have sampling, spatial sampling, smaller as 1.1 meters. And so that's almost similar to the traditional wireline logging scale. So that's what be a great advantage for the DAS tools. And for this sampling 0.1 meters, what's the gauge length you have?
Yeah, it's 1 meter.
1 meter.
So
okay.
If you the gauge lengths, the gauge lengths for DAS and spatial resolution for other instruments are so far limited to 1 meter, but we are pushing hard at the R&D stage to decrease this.
Yeah, that's great information. We just learned. Thank you so much for the Vincent. And I think if we don't have further questions, I will be hand over to the Casey to make the conclusions of this seminar.
Yes, thank you so much to Yingping for moderating and to Oleg and Vincent for their presentations today. The recording will be made available on the IRIS Earthquake Science webinar playlist. If you're interested in future DAS webinars, please join the DAS mailing list and check out the DAS RCN website. Thanks so much for joining us.